All right, everybody, this is Mr. Berry from Columbia University.
And this is Born Berry from NYU.
Okay, so today we're going to start with the good news. In the morning, we're going to host some people from England, right? British TV will make a feature on Suborna, will reveal the name of the television when the time is due. Okay, and that's very exciting news. This is the first time the British media covering Suborna's story. Anyway, so Suborna, can you please tell me, I always wonder, what is the least action, when you do the least action, right, between 2 points, what is the thing that you try to minimize?
Action. That's why it's called the principle of least action, because action is what you're trying to minimize over the path.
You try to minimize time or you try to minimize distance?
Action. Action can be anything you want.
What can it be? Time?
No. It is essentially the integral of the Lagrangian over a path. And the Lagrangian itself...
You are not in the camera, yes.
The Lagrangian itself can be anything that has the unit of energy, which means it can be the potential energy plus the kinetic energy, the potential minus the kinetic. It can be anything that has the unit joules, or the energy unit in specific. So, that means that in some cases, if you minimize the action, it gives you the same path as if you're trying to minimize the distance, while in other cases, it might give you the minimal time path, while in other cases, a minimal action path might not give you the minimum distance or time. That's what's so different about action.
So Einstein field equation, how it is different from Newtonian mechanics? Well, especially when you talk about high speed, and that's it?
Well, yeah, essentially. That's the only major difference. It diverges from Newtonian mechanics by a factor called the gamma factor at high speeds.
Euler-Lagrangian is the language for Einstein field equation, and how?
Well, I mean, the Lagrangian is simply one way to derive the Einstein field equations. In fact, it's not the way that he originally used, but it was the more understandable and approachable way used by David Hilbert to rederive the same thing in 1920.
The great mathematician who never won the Nobel Prize, but supposed to win the Nobel Prize for his contribution in physics. Anyway, my last question is, the field equation is a differential equation.
Well, yes, it is.
And the solution of field equation can be very useful. Why then it is difficult to find solution of field equation? We found many solutions, but one is very famous.
Left side of the equation is 64 different 4x4 matrices added to 16 different 4x4 matrices, all added to the cosmological constant, which means that you have a system of equations which is practically impossible to solve if you don't make very sweeping approximations or assumptions that collapse all of the terms down. So, I mean, even 2x2 matrices are hard to solve differential equations with for humans. Then, when you expand the number of terms in each matrix by 4, which additionally makes multiplying them by vectors harder, and then you combine that with the fact that, well, differential equations are differential equations, they become basically impossible to solve even with computational methods. Because, here's the thing, a computer is not trying one function. It's trying a vector function, a 4-dimensional vector function. And that could be billions, trillions, practically infinitely many different possibilities. And none of them could, and there's a possibility that none of them could satisfy the differential equation in a specific scenario. Which is why, I mean, it takes so much computational strength, and sometimes you can't even do it for the field equation.
So how did then Schwarzschild, without computer, I believe they, at that time during World War II,
World War I.
World War I, I don't think there was he had access to computer in the Russian front line.
he thought about was a spherically symmetric, no angular momentum sphere. And no angular momentum means that the term on the right side is basically zero, and it also means that many of the terms on the left side collapse into matrices that are much easier to solve. And in fact, deriving the Schwarzschild metric is a standard exercise in relativity classes today.
And that's how he found the application. Well, he got the solution, and that even surprised Einstein, right?
Well, yes, he did derive that there would be a singularity at a point where Newtonian mechanics predicted that the escape velocity of the spherical object would be greater than the speed of light, but it also took significant work to prove that, of course, since all of reality is not just one perfectly spherical, non-spinning body, it took even more work to prove that black holes could exist, and then even more work done by Penrose and Hawking specifically to prove that it was very likely that black holes existed.
Because when
because of
gravity is when the escape velocity is bigger than the speed of light. All right, so you're going to make the presentation. Which one are you going to do first?
So let's start with the principle of least action in Einstein's theory. Let's say you're solving a system like, I don't know, this. This is bad. And something like this is even worse if you're using Newtonian mechanics.
The first one is the accelerator.
No, that is a spring.
Okay.
So here's the problem. The motion of the second object entirely depends on the motion of the first object, but the motion of the first object also sort of depends on the motion of the second object, which has an even smaller effect on the motion of the first object, which has an even smaller effect on the motion of the second object, and so on and so forth. So, you eventually realize that using Newtonian mechanics, this becomes a mess that's totally unsolvable. So, you have to use a different principle. And that comes in the form of the principle of least action. Now, when we need to use the principle of least action in classical scenarios, we want it specifically to match Newtonian mechanics, which means that we need the principle of least action to reduce down to the most fundamental equation of Newtonian mechanics. Force is equal to mass multiplied by the double derivative of position. So that's what we need to reduce it down to. This, right over here. So, what do we have? Well, we take the action as, of course, being the integral of the Lagrangian over our path length, and we have this function right over here. Partial L partial x is equal to d dt partial L partial x dot, and it is guaranteed by the principles of optimization that the function x of t that comes out of this will minimize the action. Now let's think about what we need to do to make this equivalent to f is equal to mx double dot. Now here's the thing. This right here is, well, we can't actually say anything for certain. But the first thing we can do is recognize that force is actually the negative space derivative of potential. which means that it's going to have some similarities with this. And the second thing that we have to recognize is that kinetic energy is a function of the time derivative of position and not actually position itself, which means that no components of it will be showing up here. So that means that since the Lagrangian has to have the units of energy, it's going to have minus u of t right over here, and then whatever function, let's call it f of t over here, such that what? Well, it's not just going to be of t, actually. Of course, it's a function of a bunch of other things. So u is actually a function of x, and x itself is a function of t in that case. And here we have f of something else, x dot. So what is this going to be? This is going to be in terms of kinetic energy somehow. So what's this? If we plug it into here, we get force, pretty simply, because you take the negative of the space derivative of potential is equal to d dt f dot, or f prime of x dot. So, I mean, then it just seems easy enough. F prime of x dot should be equal to what? Well, we already know from the laws of Newtonian mechanics, this is equal to mx double dot, right? So now, we integrate with respect to time on both sides. And, I mean, we get something that looks like this. So, that means that now we integrate with respect to the time derivative of position, and we get, looks like this is just kinetic energy. So, through a perfectly logical process of deduction, we figured out some Lagrangian that we can use to make sure that this is equivalent to Newtonian mechanics. But, of course, as you know, Einsteinian relativity is not seeking to be close at all to Newtonian mechanics, which means that we need a new axiom. And that comes in the form of this right here. D to the fourth. So, this integral right here, well, this is actually the axiom. So, our Lagrangian would, of course, look like this without the giant integral sign. So, as it turns out, this is the only function that satisfies the unit needs for us in 4 dimensions. And it also includes the elusive Ricci tensor, well, actually Ricci scalar, which is a specific way to encode essentially how curved or distorted a space-time or manifold is. Which means that this essentially encodes the entirety of, well, how distorted a system is. And the rest are proportionality constants used to fit with experimental data or used to fit with the Einstein field equations. So then, all we have to do is use the principle of least action again. You can even use this. And so, this by itself will give you the Einstein field equations in all of their glory. And of course, what do those look like? I I believe. Yeah, I'm pretty sure this is the field equation boiled down to all of the essentials. So, as you can see here, this kappa proportionality constant is carried down below. The Ricci scalar takes part here, and the Ricci tensor takes part here as well. So, as you can see, this is a differential equation where we solve for this metric tensor right here. This right here is actually, as it turns out, a function of the metric tensor as well as a function of the change of the metric tensor. And, well, T mu nu is indirectly a function of the change in the metric tensor as well. Which means that overall, this creates an incredibly complex differential equation, especially when you consider that none of these are scalar functions. This is a matrix, actually. This is a tensor, and this is a matrix, but technically a tensor. Well, all matrices are tensors. So, that makes deriving this from this pretty complicated, but still, there are processes for it out online, so I don't think there's novel content in that for me to teach you. So, this is generally how the field equation is derived, simply from the principle of least action. All we're doing is minimizing the action. And at the fundamental core, that's a pretty simple concept to understand. I mean, you can essentially...
You want to switch to Blackboard? Because
no,
you have...
I mean... at the core, you can understand energy.
We need a little bit more audience. You want to move?
How is that going to change anything?
Okay.
In fact, less colors probably gets... If you have 2 points in a path, you can kind of visualize the Lagrangian as representing the energy of the system somehow. So it makes sense that you want to minimize it by minimizing its integral. So minimizing the area under this curve right here. In other words, minimizing its integral is the same thing as minimizing its average value, by the way. So, all you have to do is find one of those stable points, right? I mean, you could even pretend this graph is a hill and roll the ball down it. And you'll notice that it's going to settle in this area slowly over time. And that's the exact same thing that a particle will do when set at this point in the energy versus space graph. It will slowly start to gravitate towards the point of lowest energy. And that can be thought of as an application of the principle of least action. So at the core, it's all about objects wanting less energy, even though, of course, it's a little bit more complicated than that. So you can derive the Lagrangian in detail for a specific scenario for which you want to find the action, and then use that to finally derive a formula for your functions. So that's it. Thank you everybody for watching.
Did you do both?
I don't think.
2 minutes, the other one.
No.
How long is it going to take?
At least 15.
Finish it in 5 minutes because you need to practice it. You want to do over there?
Yeah.
Okay.
Oh, we barely have like good chalk anyway.
No good chalk?
No, they're all broken in half.
Oh.
So, if you want to find the shortest path between 2 points, what you want to do is...
I'm gonna go get the chalk. You continue.
You know that the solution to this problem exists somewhere out there. And of course it's actually a straight line. But you don't know what the solution is. So you call this unknown solution some perfect function y of x. And then you make an attempt. And of course this attempt is very far from being correct. And you call this attempt capital Y of x. And you attempt to quantify the difference by just saying y of x minus y of x is equal to alpha times some error function. And alpha is just some scalar that we use to scale the error, eta of x. So as you can see, in this case, the error function probably looks a bit like this. Kind of just like the regular thing being rotated a few degrees. So as you can see, this error function is, well, very different from y of x by itself. So what you'll also notice is that this error function
Look, baby.
is equal to 0 at the endpoints. Why? Well, because we're, constructing a path between 2 points, which means that the path inevitably has to include the 2 points. No matter how bad we make a mistake, at the endpoints, our function, or our path, and the original path must still share the same endpoints. I mean, if you get there the short way, and someone else gets there the unfathomably long way, well, you still shared the same start and end point. So that means that the divergence in your paths is 0 when you converge on these points. So, as you can see, given that y of x and y of x, of course, are continuous, then we can assume that this approaches 0 at the end here. But that's not really what's important. So we want to take an integral that represents our length. In this case, that's equal to 1 minus y prime of x squared dx. Why is that? Well, because if you draw, 1 plus, sorry. If you draw a very small part of this curve, you can approximate it as a line with infinitesimally small height dy and infinitesimally small length dx, which means that its slope is dy dx, or y prime of x, which makes this just dy squared plus dx squared, which of course you can factorize as dx times the square root of 1 plus dy dx squared. Which becomes this. So then, this is essentially what we're looking at. And in our case, this is actually our Lagrangian, so to speak, even though we don't use the Lagrangian in these scenarios. So this is how we represent our action, and this is actually going to be over the path length. But anyhow, what do we get from this?
Baby, I got lots of beautiful chalk. Take the most beautiful one.
Taking white because none of the other ones are going to be visible on a blackboard. So from here, what do you do? Well, given this integral right here, what are we always trying to do? Wait, actually, we can just use the Euler-Lagrange equation. Never mind. So, but no, that's not any fun. Well, yeah, you can use it. So you can let this just be some function f divided by, well, y, and this is equal to dx partial f partial y dot. This is the Euler-Lagrange equation at its core, and, well, f is this. And this arises due to a number of properties, such as the convergence at the start and end points that I mentioned before. So, what do we get out of this? Well, this, of course, becomes 0, because this is just a function of y prime of x. And you get d dx partial f partial y prime. And what is that equal to? Well, 1 over 2 multiplied by 2 times 1 plus y prime of x. Might be a little bit. So let's write it this way. Taking the derivative of this with respect to y prime is akin to taking the derivative of this with respect to x. So we don't care about like y double prime appearing or anything. So what's this equal to? This is just equal to 1 over 2, 1 plus x squared times 2 x due to the chain rule to the negative 1/2. And the same thing happens, but we just substitute in y prime of x for x. So you get what? Now, this, of course, implies that this is a constant. So, we multiply both sides by the denominator here. Square both sides. And then move around the terms so that on one side you can factor out y prime of x squared from the constant c squared minus 1, and on the other side you can just have negative c squared, which means that you figure out y prime of x squared is equal to some constant 1 minus c squared over c squared, and eventually you figure out that y prime of x has to be constant, which means that, well, the slope of our line has to be constant, which further says that it has to be a straight line, because anything else, the slope wouldn't be constant. So, this is our final statement showing that, and, well, you can do something extra. You can call this constant right here m, and then take the integral with respect to x on both sides, and then call the integration constant b, and it looks like you have a very familiar formula. That's it.